So if you want to watch this recitation with my notes at hand, so you can annotate it as I add more stuff to the slides, feel free to download it. It's on my section of the recitation page, and it says Notes Recitation 12. So today's our last recitation. So I included an extra section for the pentose phosphate pathway, but because we covered that in the last recitation, I just put it in there as additional review. But our focus today will be mostly lipid synthesis and nitrogen metabolism. And keep in mind that this is a very long set of notes because I don't think I can cover all of nitrogen metabolism in one recitation. So you guys can refer to the notes anyways, for all my notes on nucleotide synthesis and stuff like that. So in my best advice, if you're trying to find a way to make sense of all these pathways of synthesizing amino acids and nucleotides, you're getting lost on where to copy them or anything, you can refer to this PowerPoint for sure. So to start, we covered the pentose phosphate pathway last recitation, so I'm going to kind of glance over that. But just remember that there's two phases: the so-called oxidative, where we cover NADPH and ribose, and the so-called non-oxidative pathway, which uses the transketolase and transaldolase mechanisms we talked about last recitation. So hopefully those are still memorable for you guys, as this might be important in addressing reactions that involve changing carbons from shifting carbons two at a time between molecules. And then we left off also with, depending on what the cell needs, the cell might proceed with a different pathway. And so this gives you an idea that it doesn't matter that we have a pathway. Not all pathways are run the same way. Sometimes the cell can redirect its resources to one particular pathway depending on what it needs. And so hopefully this is still memorable from that. So we'll start off with lipid biosynthesis. And the first thing I want to say is hopefully you remember lipid breakdown or fatty acid oxidation. And we remember that that process is kind of every 2 carbons. So in this case, we remove 2 carbons at a time in the form of acetyl-CoA. In lipid biosynthesis, it's kind of very similar. We add 2 carbons at a time instead. And so we're going to show that process. And so I put here on the right the pathway for fatty acid synthesis. We don't need to go into depth about each step yet, but in the next coming slides, I'm gonna retain this so that we can kind of have a map of where we are in the reaction. But here are some key guidelines that you should remember when you think about fatty acid synthesis. So as I said, it starts with 2 additions at a time. And so if we break down 2 at a time, we also add 2 at a time. So that's a key part in here. The other thing is that in oxidation, we harvest energy. And so in synthesis, we have to spend energy. And so in this case, a source of energy that we use to make fatty acids is in the form of ATP and NADPH. Now, keep in mind, we don't use NADH. The idea is that the cell uses these 2 differently. NADH is used to harvest energy. So in this case, the NAD is used to pick up electrons, whereas the NADPH is used to reduce. And the reason for that is that we want the NADH to NAD ratio small so that we encourage the oxidative process, whereas we want the NADPH to NADP positive ratio high so that we encourage the reductive process. So that's why we use 2 different carriers. It's not just for 2 carriers for 2 pathways, it's more of we don't want them intersecting with each other. Usually when we elongate a molecule, we stop at 16 carbons, and then a different process in the peroxisome will continue after that. So all of our analysis will only really contain to 16 carbons. This happens in the cytosol. So this might be a problem later on when we talk about where does the acetyl-CoA come from. If you're going to make a double bond, it is naturally cis. And lastly, I put in here the general accounting for what the cost is of adding 2 carbons, but we'll go over exactly why. So right now it doesn't make sense to kind of just show you this, and we'll cover this again later on. There's a lot of enzymes because there's a lot of steps. And so it's not super important for you to remember each enzyme name. But the whole thing is generally described as the fatty acid synthase. So in my opinion, you don't need to memorize each of the enzyme names, just call them fatty acid synthase, and maybe remember the acronyms for them if you want to make it more specific. So let's look at the first step. So the first step we're showing here is acetyl-CoA and malonyl-CoA. So we first need to start making that. Acetyl-CoA, we already kind of made that through maybe your TCA cycle or your pyruvate decarboxylase cycle, or if you broke down fat. So acetyl-CoA, we already know where that came from. So this could come from fatty acids. This can come from your pyruvate, or it can come from amino acids. So specifically an amino acid that can form acetyl-CoA is pyruvate, sorry, not pyruvate, alanine. And so those can be the sources of acetyl-CoA. So the first thing is acetyl-CoA sticks to the fatty acid synthase by binding to this site called KS. Do you need to know that this is the name? Nope. But just for geography, so that we don't just say that it's attached to somewhere, we're going to say it binds to the KS domain. And so that is why we call it ACP. And so we have acetyl-CoA bind to that region. That's the first step. Essentially, think of this enzyme complex, the fatty acid synthase, as a factory for making fatty acids. And so we first attach acetyl-CoA. And this will be our 0 point. So think of a growing chain. This is the first part of the chain. So that's the first step. So we got that part done. Now let's move on to the next step, which is the malonyl-CoA. Now, before we say we attach malonyl-CoA, we also have to talk about how do you even make malonyl-CoA. And so to make malonyl-CoA, you actually make it from acetyl-CoA. And so without looking at the mechanism in the slide, let's look at the differences between the two. Acetyl-CoA has 2 carbons, whereas malonyl-CoA has 3. And so this reaction, hopefully you realize, because there's only 1 carbon difference, this should be a carboxylation. If it was 2 carbon differences, maybe you suspect maybe one of your transketolase transaldylases, but because it's only 1 carbon, most likely it's a carboxylation. And so this mechanism you've learned already. Whenever you carboxylate something, you have to use a couple of reagents. So if I were to write this on the exam, acetyl-CoA turning into malonyl-CoA, the reagents I would need are first CO2, because that's where the carbon comes from. I need a biotin, and then I need ATP. So, and that is shown here, where you have a bicarbonate, and with the power of ATP, where you form carbomoyl phosphate, you have it attached to the biotin, and then the biotin will attach it to the destination, which in this case is acetyl-CoA. If you want to see the electron pushing of this, it is located in the recitation that covers gluconeogenesis, because this was a mechanism relevant to that. And so feel free to check that section. So after we carboxylated acetyl-CoA and form malonyl-CoA, we then attach it to the complex. And so essentially, we attach malonyl-CoA to this top section right here. And so you have the acetyl-CoA in the KS section, and then the malonyl-CoA in the ACP section. So we have now successfully described these two. So now that you know where these come from, let's actually proceed with the reaction. The first thing is condensation. So they need to combine together. And so that is powered by a decarboxylation step. It kind of looks weird because we took all that work to carboxylate acetyl-CoA to form malonyl only to get rid of the carbon dioxide. So it doesn't make sense from like a perspective like that. But I like to think of this as the whole point of carboxylating malonyl is to charge it with energy. And then that energy charging will power the condensation, because condensation is an energy needing process. And so this decarboxylation powers that reaction. The exact electron pushing is as follows. You decarboxylate and the electrons just attack the carbonyl. And in the process, you've also remove this acetyl-CoA from its binding site. And so you can call this a condensation because the two things are coming together, but also you can think of it as a substitution because this acetyl-CoA swaps partners from this sulfur group to now this CH2 group. And so that's the first step. And the one thing you should just remember from this first step is that this is a decarboxylation step, so a byproduct is also CO2. And note that at the end of this, the product is now at the ACP domain. So it's like, if you look at this geometry, it is now attached to this top part. This is going to be important because now once it's attached to this top part, this substrate can now circle around the enzyme and in the synthase, the complex. And at each section, there's going to be a different reaction, which is going to basically allow us to run through the entire pathway in one swing instead of using multiple enzymes. So after they condense, this is the product, aceto-acetyl ACP. Do you need to know the name? Not really. But basically, it's now 4 carbons. So we've accomplished the first goal, which is to make a longer chain. The next thing we want to do now is get rid of this O's because we want to have a fatty acid, which is mostly just carbon and hydrogen. So to that extent, we have to reduce. So the reduced form of a carbonyl is an alcohol. So we can just actually do that directly. We can have, in this domain, a NADPH come in and reduce this carbonyl right here and turn it into an alcohol. So that's the first step. We've reduced it once by turning carbonyl to alcohol. Now, can we reduce an alcohol even more? So technically the answer to that is yes, because a more reduced version of an alcohol is just if you get rid of the O and turn it into a CH2. However, that would imply that the OH needs to leave, and OH minus is not really a good leaving group. And so that reaction is a little unfavorable. And so to circumvent that, the next step we're gonna do is dehydrate this molecule. And so we take this, and hopefully, if you're checking 512, maybe a review for your mechanisms. But if you have already taken 512, then maybe a review of that. Hopefully you remember that if you have this, you can reverse that by dehydrating it and turning it into an alkene. Basically get rid of an H2O molecule. And so we're going to do exactly that. We're going to take this OH and 1H and get rid of that. And in the process, we'll form a double bond. And so why do we bother doing this again? Well, it's because this alcohol is not reducible with the current circumstances because of a bad leaving group. But if we turn it into an alkene, we can reduce it without having to worry about a leaving group. And so we basically dehydrate it. And then once we form this double bond, we can reduce it one more time with NADPH. And when we reduce that double bond with NADPH, we get now an alkane, CH2, CH2. And so that whole scenario essentially circles around the enzyme. And so we go around condensation, reduction, dehydration, reduction again. And so your final product is now this molecule right here. So that's one cycle. That's what happens in one cycle of the fatty acid synthesis. Now, how does this look like from a larger perspective, when we're talking about growing a 16 carbon chain? So after it's made one cycle, this, oops, sorry for clicking forward. This fatty acid right here is actually going to migrate to the KS domain. And after it migrates to the KS domain, this will now be empty. Well, now that it's empty, then a new malonyl-CoA can come in. And so essentially, whenever there's a cycle that's done, it will move to the KS domain, which is, again, kind of like a location for the older chain, the chain that's already been built and will be added onto, whereas the new malonyl-CoA will come into this section of the ACP instead. And so if I were to provide an analogy, think of the KS domain as kind of like the P site of the ribosome. It's the one that holds onto the growing chain, whereas the ACP here can be thought of as the A site where the new amino acid comes in. So in this case, the new malonyl-CoA. So to give you a better drawing of that, let's look at it from a different perspective, like this. So at first addition, we have, so think of this long chain as the ACP and the small chain as the KS. The acetyl-CoA binds here, the malonyl-CoA binds here. When the two of them condense, you notice that first the acetyl-CoA moves to this end, and then it goes through the series of reductions, and then the whole complex that was made will re-move to the KS domain. And so after that, you see here in the addition of the second carbon, that the two carbons are now on the KS domain, with a new malonyl-CoA ready to be added. And now if we imagine that getting added to this end again, and then after the reductions get moved again, you can see at the third addition, we have all of them of the growing chain located in the KS domain. So essentially what this tells us is it can tell you the age, if you will, of each two carbons in the fatty acid chain. If I have a growing chain like this, the oldest carbons, so not old in the sense of like timeline, but more of like which one was added earliest, the oldest would be the most omega ones. The most omega carbons will be the ones that are added first, whereas the most earliest ones, one of your alphas and everything, these will be your most recently added carbons instead. So hopefully this is helpful in case Vander hadn't asked you a question where, let's say, he'll give you radio-labeled carbon at whether the beginning or the end of a fatty acid synthesis. And so it's important for you to understand, if you add label in the beginning of the synthesis, would you see the label in the end of the fatty acid right here or the end right here? And so that's helpful to remember. And to think about the accounting once more, hopefully you guys remember that there was two NADPH steps and one ATP step. So the ATP step was for the carboxylation, whereas the two NADPH steps was for the reduction. And so to give you a sample problem, if you have 16 carbons of palmitate you want to make, then the first thing you want to realize is that that needs 8 acetyl-CoAs. And if you have 8 acetyl-CoAs, then that means there's 7 bonds in between them. And so that means you need 7 reactions. And if every reaction needs 1 ATP and 2 NADPHs, then you just multiply that and you get that the cost of making palmitate is your 8 acetyl-CoAs, 7 ATPs, and then 14 NADPHs. Now, this is nice. If they tell you that they provide acetyl-CoA, this is your final answer, 7 ATP, 14 NADPH, perfect. But there's a cost that we have to consider in the fact that fatty acid synthesis occurs in the cytosol, but the acetyl-CoA is made in the mitochondria. So remember, pyruvate to acetyl-CoA is made in the mitochondria. So there's this transport cost that needs to be taken into account. So actually the cost of transporting acetyl-CoA from the mitochondria to the cytosol, it needs 1 ATP. And so if you want to take that into account, then every acetyl-CoA needs to have an extra ATP cost to it. So if we have 8 acetyl